So now we are learning about the second Momo method. Then last time we defined binomial random graph model, GNP. So this is a probability distribution where we get graphs with certain probability. So the resulting graph we get has a vertex set which consists of the vertices from 1 to n. And for each pair I and j, you flip a coin which comes up with a head with probability p, and then tail with probability 1 minus p. And then if this is head, then you add an edge, otherwise you don't add an edge. You do that independently for all pairs. Then this, will give you a graph. The number of graphs you can get is 2 to the n choose 2. It's a labeled graph. So we consider this 1, 2, 3, and 1, 2, 3. So these two graphs are different graphs. So we have this many graphs, and each one of them has a certain probability of appearing. That give you a probability space over the all possible n vertex graph. That probability space is this binomial random graph model. And we say that this binomial random graph satisfies certain property, with a high probability. That means the probability that it satisfies, the resulting graph satisfies certain property is, approaching to 1 as n goes to infinity. Then we said that it's a with high probability event. And we say that the certain function is a threshold function for some property p. If whenever this probability p is going to, it's much smaller than this threshold function. If this is much smaller, then the G does not satisfy P. The probability that it satisfies P goes to 0. And then if this probability is much bigger than R, then the GMP almost always, with high probability satisfy P. And we want to find the threshold function for certain property. So let's consider some easy cases. So it's not really so difficult to show that okay. So here, so we are assuming that for Rachel property, Rachel natural graph property, this property is satisfied by dense graph, but not sparse graph. So many natural properties are like that. So for example, if we consider G and 0, then this is empty graph. And if we consider G and 1, then this is complete graph. So for example, in this case, if we want to say find certain subgraph H inside of G, and as long as H is not empty graph, it contains some edges, then with probability 1, this does not contain any H, but with probability 1, it contains H. So if we see the probability of G contains H as P is from 0 to 1, it's 0 here, and here it's 1. So, and our intuition tells that as P increase, it must increase. So it must be something like this. And we might wonder that, okay, then, how does this actually behave? Does it go in this way, or Or does it go rather in this way? So at certain point, before that it was almost 0, but after that it's almost 1. So something like this. I mean, in that case, we have some threshold function. So which, I mean, both of the case could happen. Or even it could be like it's almost 0, and at a certain point it, I mean, spike up to half, and it stays there, and then at a certain point it spike up again. So this could happen. So we don't know which is the case. And the answer is that so it's actually later in the book, and I'm not quite sure whether we will cover that in this lecture. The lots of many natural property P has a threshold function. So many natural graph property, actually, if you, I mean, map it on this graph, then it mostly looks this way. So it's mostly 0 for lots of, I mean, interval here, and at a certain point it spikes up to 1, and then it stays there. So lots of natural graph property has a threshold function. So let's consider this, I mean, property P, which is having certain subgraph H as a subgraph. But not, I mean, arbitrary H, but we want to consider the following H. So let H be a graph with n vertices and e edges. And we call the density of H as the number of edges divided by the number of vertices. And we call H balanced if we have that every subgraph H prime has a smaller density, smaller or equal density as H, and we call H strictly balanced if every subgraph H prime has a strictly smaller density. So we are considering this because, okay, considering these two cases, so this is H and this is H, then in order to get this, I mean, so if we have this threshold function for the, I mean, for the property P having H as a subgraph, then obtaining this must be more difficult than obtaining this. Because if you already have this, then it implies also, I mean, having this as a subgraph. So this suggests that if H is denser, H has more edges, so in terms of this density, if H has a higher density, then it must be more difficult to obtain. That means P has to be higher. This P has to be higher. The P that the GNP started to have this as a subgraph should be higher or equal to the probability P that where GNP started to have this as a subgraph. So our intuition is that if the graph is denser, then P must be higher. But that's not the only thing. If we consider again this and this, say then this has 5 edges and 4 vertices. This has 18 edges, 16 vertices. So this is 9, 8. So this is actually has a higher density. This has higher density than this. But obviously, if you have this as a subgraph, then you also have this as a subgraph. So obviously, this is more difficult to obtain than the one on the left. So having this as a subgraph must have a higher threshold function. But the density is the other way around. So maybe we can think that our initial intuition of having higher density is more difficult to obtain might be wrong. But that's not the case. The reason why this has a low density is because of these parts which lower the density. Without this, if you just consider this middle part, it has actually a higher density. So we want to, formalize our initial intuition of having higher density is more difficult to obtain. We don't just consider the density itself, but we want to consider the density of the densest part. So, there are, several ways to actually formalize this, but in order to just avoid the situation like that, the simplest way is that we call certain graph balanced if the situation on the right-hand side does not happen. And then we only consider about those for now. So that's the motivation of this balanced. Definition of this balanced. So now our goal. We want to show that if H is balanced, then we want to show that n to the negative v over e is the threshold function. Actually, it's a threshold function. Because to our definition, if this is a threshold function, then twice of this is also threshold function. Or, 3 times of this is also threshold function. So this is a threshold function. So for this, we want to, prove this theorem. So let H be a balanced graph with V vertices, E edges. And say A automorphism. And let X be the number of copies of H in GMP. And if P times N to the V over E is little of 1, then this means if this goes to 0 as N goes to infinity, then X is 0 with high probability. And if P times NVE is omega of 1, which means this goes to infinity as N goes to infinity, then we have X equal to 1 plus little of 1 times N to the V, P to the E over A with high probability. So this is just restatement of, this with a slightly more information. So this is a threshold function, just means that this is 0 and this is strictly bigger than 0 with high probability. But here we can actually, estimate this x for this case. So before proving this, obviously we want to do two things. So for the first case, we want to just show that the expectation of x is very small. Then we can actually conclude this. But for the second case, expectation alone is not enough. We want to also show concentration, that its expectation is actually this, and then it's very concentrated. So it's close to this with high probability. And for the concentration, we want to measure the variance and then show using the Chebyshev. And if you restate the Chebyshev, then it can be actually restated in this way. So if you just plug in, so what was the Chebyshev? This is the Chebyshev. So you write the lambda as a, sigma over epsilon mu over sigma. Then, you can get the above inequality. So, oftentimes we want to just show that x is concentrated over its average, and then error term is just little of 1 times this. So, which is essentially smaller than the epsilon n times the expectation, epsilon times the expectation. So this is essentially what we want to show. It is concentrated around its expectation. For that, we need to show that this goes to 0. So we wish to show that this variance is little of expectation square. So if this decay is much faster than the expectation square, then we can make sure that this is also, smaller than what we want. So for the second statement, we, actually will show this and then apply the Chebyshev to conclude. So let's first show the, first case. For that, we need to define certain, random variable. Again, what we want to do is, this is random variable. We want to decompose it into a simpler random variable. Actually, the indicator random variable, which sums up to this x. For that, let's say the vertices of H is 1 to V, and for each ordered tuples, say x1 to xv of vertices in G, which is G and P, we let AX be the event that this x1 to xp actually provides a copy of H in that order. Meaning that if H was 1, 2, 3, then A, x1, x2, x3 is a probability that you have x1, x2, x3. You have an edge between these two, and you have edge between these two. Here, there could be edge, there could not be an edge. It doesn't matter. Even if this happens, we say that this event is, happen. And even if this case, we say the event happens. But here, we actually care about the ordering, meaning that if we have x1, x2, x3, and then this is not an edge, then we say that this didn't hold. Because if you, 1, so there should be an edge between x1 and x2, and 2, 3, x2 and x3, but this didn't happen. So A, x1, x2, x3 didn't happen, but A, x2, x1, x3 did happen. So this happened if we have this. Because x2, x1, x3 actually form this copy of H in that order. So that's how we define, and let I x1 to xp be the indicator random variable, which is 0 or 1 if these events hold. If this happens, then 1, otherwise 0. But with this, there is slightly inconvenient. Let's say this is H. Then A, x1, x2, x3, if you have x1, x2, x3, and x3, x2, x1. If we have this graph, then these two events hold. And you can actually check that those two are the same event. So they actually, are considering about the same event. So we want to identify those. So X is X1 to XP, and Y is Y1 to YB are the equivalent if Y sigma I is Xi for some automorphism sigma of H. So, these two are same event, so we also make this ordering, this order tuple equivalent. Then X is same as summation of X, this indicator random variable over all this, where this subscript runs over all equivalence class we just defined. So for these two, we just add one. Then what's the expectation of X? This is summation of all this, and then each of them, the probability that this happen is P to the E. So there are E edges. So we have this, then we want this pair and this pair to be there, and that happens with probability P and P, and they are independent, so this is P squared. So for general H, there are E edges. So the probability is P to the E. And how many equivalence classes are there? The number of this tuple is n times n minus 1 times n minus b plus 1. And then there are A tuples, because for each automorphism of H, you get another one which belongs to the same equivalence class. So there are A many of them are forming equivalence class together. So this times P to the E, which is 1 plus little of 1 times n to the B, P to the E over A. So Now we consider the first case. If p times n to the b over e is little of 1, then what do we get? Expectation of x is little of 1. But by the definition, this expectation of x is, so note that one of the properties that this x has an integer value, non-negative integer value. So this is same as the summation of I times probability that x equals I, and this is bigger than the probability that x is at least 1. But this is little of 1. That means the probability that x equals 0. So if this is not at least 1, then this means this is at least, this is exactly 0. Is 1 minus probability of this is 1 minus little of 1. So with high probability, we have x equals 0. So now we have to consider the case where this goes to infinity as n goes to infinity. So we will prove that case in the next video.